Good afternoon, everyone. My name is Ricardo Lopez, part of the University of Michigan, and today's talk is going to be on neutron and gamma imaging with a novel organic glass-based imager. I'll begin by talking a bit about the motivation behind our work, and this has to do mostly with the concerns in the field of nuclear verification and non-proliferation, particularly in accounting for nuclear materials, since we don't want it to be end up in the wrong place. And the way we seek out to answer this and address these concerns are by developing deployable instrumentation that can go out into the field and resolve some of these issues. One of the big things we have in mind, though, is we wanted to have a very small form factor to keep in mind user-friendliness. You can have like one of the best systems out there, but if it's too bulky or too big to carry around and take it to the place it needs to go, then no one's really going to use it, and we don't want that. So we set out particularly looking into particle imagers, since they've already proven a useful tool in the field, and they have the important capability of being sensitive to both the neutron and gamma signatures of uranium to plutonium, which is something that we really want to take into account. Novel organic glass insulation material, or OGS, has recently been developed by our collaborators over at India National Labs, and it has very high light output and detection efficiency, especially compared to more traditional materials, which means that we want to try to use this for a particle imager for the first time. And it could be melted down and cast into a variety of geometries, such as here in the bottom right, where that could be also be very useful depending on the situation. The NNSA's mission relevance in regards to this project mostly has to do with two offices, namely NPAC and the Office of Nuclear Verification, both of which would very much benefit from equipping personnel with particle imagers that are capable for source isolation, particularly to detect and deter the diversion of any nuclear material, and source identification, which would be very useful for monitoring and verification purposes. The actual active volume of the imager itself is composed of 12 organic glass bars of 6 by 6 by 50 millimeters cubic volume. The picture on the right shows them, which would be right there in the middle of the system. You can see that they're white, and then that's because they're wrapped in Teflon in order to improve the light output collection. We also use 8 serum bromide inorganic scintillators to help improve overall the gamma efficiency of the system. And all of the components are coupled in between SiPM arrays for the data acquisition. The OGS composition itself that was developed by our collaborators over at India is sensitive to both neutron and gamma rays, which is very important to us and why we sought out to develop this type of imager. What we will actually be doing is reconstructing double scatter events that occur within the active volume of the system, and then ultimately apply a converging algorithm to better determine the most probable location of the source. I'll begin a bit by just showing how the actual mechanisms for the imaging works. To begin, the gamma imaging of the system works by first having an instant gamma ray Compton scatter within any of the 12 organic glass bars. And then the second event would have to be a photologic absorption in one of these serum bromide cylinders. Summing up the two deposited energies would give the instant energy of that gamma ray, and we can also calculate the incident angle of that gamma ray, which we can then project onto a sphere to create a cone for that double scatter event. If we add several of these cones, we ultimately converge on the most likely source location. Very similarly, neutron imaging works almost in the exact same way, except now the neutron just needs to scatter in between any two separate organic glass bars in the system. And again, we collect the relevant information such as position, energy, and time. We can calculate energy, time of flights, and from that, calculate the incident angle of that neutron. The imaging experiments that we'll be talking about for this talk are concerned with gamma ray measurement and a neutron measurement. Before I proceed, I'll just reiterate that for the rest of this talk, when I refer to the directions at which sources were placed at, what I mean is the azimuthal and the altitude on all in reference to the front of the system. So for the gamma ray measurement, we have a cesium source and a sodium source, both of which were placed there plus or minus 50 degrees and level with the system. And the main reason for this measurement was just A, to verify that we can image gamma rays, and B, to show that we can isolate between two simultaneous sources in the same field of view. The neutron measurement has a similar premise. We have, in this case, two neutron sources, and we also placed the cesium source to the right in order to make sure, to show that we'll be able to distinguish between neutron and gamma sources, even if all are in the same field of view. To begin with the gamma ray localization results, if we apply energy gates to the expected gamma ray emissions for a particular source, in this case 511 from the sodium source and 662 for our cesium source, then we are very quickly able to isolate and distinguish the two sources. In this case, upon data acquisition, we're able to, within 18 seconds, differentiate between the sodium and cesium sources. And this is just with a simple back projected image. So we don't even apply some of the more complicated converging algorithms that we would normally apply to get a more converged source. And on that topic, if we measure for a longer period of time and apply our converging algorithms with the same 511, 662 energy gates, then we very nicely converge to the expected location of our sources, shown here with the sodium and cesium images. And then if you compare the actual locations of the sources as opposed to the converged numbers, which were just obtained by getting the maxima of the image matrices, then we see that there's some very good agreement. And this is also shown by the black outlines that you can see in the pictures that show where these sources would be actually located during the measurement. The neutron imaging and spectrometry results are as follows. For the actual imaging, we very clearly can distinguish two separate neutron sources, and we don't see anything where the cesium source was placed, which makes sense. It's not a neutron emitter, so we shouldn't expect to image anything on that. The actual and converged locations are in fairly good agreement. And then finally, the neutron spectra extracted from the two regions, in this case, region 1 corresponds to the plutonium beryllium source, region 2 corresponds to our californium source. We see that the neutron spectra for the PUBI is harder, so we have a lot more higher energy neutrons, and this is shown by the average neutron energy that we obtained from the two sources, 333 MeV for the PUBI and 2.8 MeV for the californium, respectively. The expected impact of this work, should it prove successful, is that it would serve as a very significant first step in the implementation of more accessible imaging systems, which would in turn be used in safeguard scenarios. The lower costs and high manufacturing scalability of OGS material would also mean that these kinds of systems would be a lot more commercially viable. And then finally, the success of this work can hopefully introduce more people to organic glass itself, who may in turn could find applications for this material in other areas that weren't explored in this project. So in conclusion, the results demonstrate the feasibility of a compact dual particle imager based on an active volume of OGS. We were able to localize two distinct gamma sources within 18 seconds. And we're also able to discriminate an alpha N source from a spontaneous fission source using some coarse neutron spectrometry. This work positively impacts NNSA's mission by developing equipment to localize sources for the divergence of material, which corresponds to NPAC, and characterize sources for on-site monitoring, which would be useful for the office nuclear verification. Ongoing work includes imaging highly enriched uranium and depleted uranium. Since thus far, we've just been doing some of our lab sources here at the university, but we also seek out to apply some protective coatings on the organic glass in order to maintain its performance over long terms of time. And then finally, we're working on better characterizing the light output function for the glass. Future work will include a collaboration at the National Criticality Experiment Research Center at the device assembly facility, where here we'll be able to measure several kilogram quantities of special material with the organic glass imager for the first time. So that's pretty exciting for us. I want to thank MTV for their help in providing some of the unique opportunities over the course of this project, such as some lab visits over to Sandia National Labs and measurement campaigns at other facilities like Savannah River and the Nevada National Security Site. We plan on continuing our collaborative relationship with Sandia, but are also open to more national lab or university collaborations in the future. Finally, we'd like to thank the NNSA and DOE for their continued support for these research activities. Thank you.